In this video, we are going to define and determine the dimensions of a matrix. We're going to define and determine the rank and nullity of a matrix. So we're going to first start out with the theorem that says, suppose S is a set of vectors, and it's a finite set of vectors, which spans the vector space V. Then any set of t plus one or more vectors from V is linearly dependent. This theorem tells us that if you have m vectors from Cm, there will be linear dependence for any vectors beyond that, and this applies to any vector space. The next theorem we're going to look at is the basis of identical size. Suppose V is a vector space with a finite basis B and a second basis C, then both B and C are the same size. Now we know from previous examples and what we worked in class is that you could have two bases for the same vector space that may not match exactly, but the size of them has to be the same. So let's define when we're talking about a size. So suppose V is a vector space where have V1 to Vt is the basis. So that means they're linearly independent. And then the dimensions of V is defined by the d of V is equal to t. If V has no finite bases, we say V is an infinite dimension. Let's start with an example. Now, suppose we have S as a subspace of R5. That means that we should have 5 entries. So here's my span. I'm going to try to define the determinant, or find the dimensions of S. Now, it is not necessarily linearly independent for it to be a span. It has to be for a basis. But this is just a spanning set, so it doesn't necessarily have to be linearly independent. What I do know, however, is that the dimension has to be 4 or less. And it has to be 4 or less because I have 4 vectors. And it could be less because we don't know if these are linearly dependent or independent. So the first thing we want to do is check for dependence. And of course, the way that we do that is we put them into a matrix and redo the equivalent row reduced echelon form. We can see in this example that I have a pivot in the first column and I have a pivot in the third column. That means only the first vector and the second vector are linearly independent, and the other two vectors can be formed by a linear, a scalar multiple to get to the other ones. Therefore, since those are the ones that are linearly independent, my dimension is 2. There are a couple of other theorems that come from this section, and the first one that is important, the outcome anyways, is if you have a dimension of Cm, it is m. If you have a dimension of r, this is a real numbers, r likes 3, it is n. I don't know why I have an n there. Maybe I just really liked n or something. And then the dimensions of our polynomial space n has to be n plus 1 because we have to include x naught. We have to include the constant. And of course, the dimensions of a matrix that is Mn is m times n. If we want to find a basis for the null space that includes x1, and then we're also going to determine the dimensions of the null space. So the first thing we're going to do is we are going to put this matrix, not including this matrix into a row reduced echelon form type of equivalent matrix. And then when we do that, we're going to find that our dependent columns, or the ones where the pivots are 1 and 2, and the ones that are the independent or free variables are 3 and 4. So 3 and 4 are linearly dependent on the first two. And then I get my null space. Now my null space then is 1, negative 1, 3, 0, 2, negative 3, 1, 2, 0. And that is, of course, based on the fact that when I do my reduced row echelon form, I'm actually going to end up with some fractions, and to make my life easy, I'm just going to multiply those fractions so I don't have to put fractions in here because I like the integers. And I'm going to, if you're checking this at home, I multiplied by the lowest common denominator in both of those, that scalar, so that I could work with integers and not fractions. Now we have to determine if x sub 1 in this null space is linearly independent. And we also want to know what the dimensions are. So I go ahead and I take my x sub 1, that's this right here, and these are the other two vectors that I found for my null space. And we can see when we put this into the equivalent reduced row echelon is that we see that our pivots are in columns 1 and 2, so x sub 1 and our first vector. So we know the last column is a linear combination of these two vectors, and so my basis is my x sub 1, and then of course my basis of my null space, I should say. The basis of my null space is x sub 1, and then I use my first column. That's only because I was asked to include x sub 1, not necessarily because I had to necessarily change it. I'm just asked to include it, and my dimension is 2. Now let's define what the nullity of a matrix is. Basically, what the nullity of a matrix is the dimensions of the null space. In this example, it was 2. We have a nullity of 2. The rank of the matrix is the dimensions of the column space. And that is, of course, the number of linearly independent vectors that I have. In our last example, our rank was 2. We had 2 linearly independent and we had 2 linearly dependent vectors. So graphically, the rank is the space spanned by the basis, right? So how many vectors do you have in your basis? That is the rank. So if we take a look at an example visually, graphically, if I'm trying to determine the rank of this where I've got 3 different planes come together, then you can see that all 3 of the planes share this line. Because they all share this line, they must have a rank of 2, because a line has 2 variables, x and y, as an example, or x sub 1 and x sub 2. So this must be a rank of 2. This brings us to the following theorem. It says that the rank plus the nullity is the columns. That gives you the number of columns. Now suppose A is an n by n matrix, then the rank of A, which means the basis, the dimensions of the basis, plus the dimensions of the null space, the nullity, must be equal to the number of columns you have in your matrix. Now that brings us to non-singular matrices and what that gives us. So let's revisit non-singular again. We're starting to really tighten up what it means to be a non-singular matrix. So suppose A is a square matrix of size n, then these are all equivalent. A is non-singular, the rank of A is n, and the null space, and the nullity of A is 0. So that brings us to our 6th round of non-singular matrix equivalence. We're really tightening up what this means. So these are all equivalent. Row reduce, A must row reduce to the identity matrix. The null space of A contains only the 0 vector. The linear system has a unique solution. The columns of A are linearly independent. A must be invertible. The column space of A, Cn, must be Cn. The columns of A are the basis for Cn, or R if we're talking about real numbers. The rank of A must equal the number of columns, and the nullity, in other words, the dimensions of the null space, must be 0. And that's it for this video.